what things you should pay attention for the mass spectrometer. So what you pay attention for the mass spectrometer, mass spectrum is, yes, molecular ion peak, yes, you do see that. But what other fragmentation happens is going to reveal the structure of the molecule. So when you should have a practice of when you see the molecule, the structure of the molecule, you should try to imagine what would be the fragment you see in the mass spectrum. Try to predict what you will see, and then you have a mass spectrum there, you can try to match it and try to explain how those things are showing up. So we're going to do a series of an example to pointing out that what you should pay attention. This molecule here is a 1, 2, 3, 4, 5, 6. So it's hexane, but it's a branching form, not a linear formation. So how that branch pattern will change the spectrum is what we're trying to say. First of all, yeah, the whole thing is a molecular weight of 86, but molecular iron is 86 going to be there. It's a very small, most of the right-hand side thing. We're going to see the fragment. We can think about what about the methyl going up? We already know that methyl radical is a bad thing, but let's just try to imagine that else. I mean, if it happened, they've already produced. The methyl group's taken out. This whole thing at the cation there, that's going to make it 1, 2, 3, 4, 5 pentyl cation, right? So that will show. We can also break that one. If we break that one, we got the ethyl radical, and then we got this butyl cation. Between these two, which process is a favorite? Are they going to make a more pentyl radical cation or make a butyl cation? For the stability of the cation side, this is a primary cation, that's a primary cation. So we are not saying any difference in energy at the cation side. But the radical side is a methyl radical, this is a primary radical. So primary radicals are more stable. I think breaking down this one happens more than breaking down that one. Because of that, you got to look at the whole thing, not just cation side, or not only the radical side. The sums of both will make an influence of each bond they create. But that's not the only bond you can think about. This bond there also can be killed out. If you break down that bond, then you get the propyl radical. Then this becomes what it does. It's a secondary carbocation. Right? So far, looking at the primary carbocation, you need to remember the ranking of the primary carbocation and carbocation stabilities. The carbocation is the same thing, it's electrodeficient species. The more alkyl chain it has, it gets stabilized better. So the tertiary carbocation is the best, then secondary carbocation, then primary carbocation. So these being secondary carbocation means that these are more stable than even that primary carbocation. What it means is breaking down this bond happens a lot more than breaking down this bond or even that one. Right? So because they produce secondary carbocation, and then it makes a primary radical, which is kind of same as that. So whole thing makes it look a lot better for that breakage right there. So what that means is you're going to see the peaks of 43 showing up pretty strong because it makes a secondary radical there. So this is the mass spectrum of that molecule. 86, yes, we do see the molecular ion peak. And then we do see the M-15, that one there. I mean, there. And then we do see ethyl, this one, that breaking that process down there. And then the biggest peak is 43, which is this one. So at least the base peak, the biggest peak, can be explained out. It breaks this one, this bond there, it makes a secondary radical, and then that's what they show. But look at these two. What am I missing? Because I predicted taking out the methyl is a bad thing because you get the methyl radical there. Ethyl radicals are a lot better because the primary radical, this peak should be higher, that should be lower. So why the methyl, I mean N-15 peak, why that is a higher than the other one? What mistake did I make? Yeah. There's another methyl group there. You gotta look at the structure as a whole thing. See that methyl, if you take it out, if you click the methyl groups out, that also makes a secondary carbocation. So this is not the only methyl groups you can take it out. You can take out that one, make this one. That's the same thing as the other one. So point is, when you try to analyze structures, don't try to trap in the how you see the structures. Sometimes there's other choices. So anyway, both signals are big because of this methyl group goes out. I know methyl radical is bad, but secondary carbocation is compensate that. So the whole thing is actually better than making primary radical primary cation. Secondary cation and making methyl radical is better than making a primary cation and primary radical. So that's why these peaks are higher than the other one. All right. So you got to look at the things very, this structure really influences how they fragment. So that's why this is where you're gonna look at to solve the structures. All right. But remember that. Oops. I just want to point out that these things, breaking this bond, make the most stable cation. That's the one that shows the highest, right? I want you to see that first. And then I'm going to ask this question. What would be the most stable fragment coming out of this molecule? After you see the first one, this one almost looks like what we just talked about, right? So just breaking that one there, make the same 43, the propyl secondary carbocation, right? Secondary carbocation, we point out that that's a good thing. And then when you break this bond, you create a secondary carbocation. So that's supposed to be good. So most likely you're going to say that yes, this bond breaks and you're going to have that. There's an issue there. The vinyl radical, which is not very common. So this is not something that you normally see. But that is not the reason. The most stable cation after breaking up, that's a fragment, you got to look at the structure very carefully. Having methyl groups here, having methyl groups there, similarity doesn't really mean anything. You really have to look at the whole thing and try to figure it out. This is an example I want to point out that this one and that one looks almost the same. Close it up. You learn how to solve this one, you memorize it, you apply the same solution to the other one there, like a breaking that bond. And you're going to point out that yes, that's a fragment, the most stable fragment, and then I'm going to say, no, that is not it. So what else should we consider? Things that we've been talking about. Taking off the methyls are so bad. It makes a methyl radical. Methyl radical is bad. I've been saying it all the time. If you just memorize that, then you're not going to take the methyl groups off because that's a bad thing. But everything has to be taken as a whole. You have to think about breaking that one off. That methyl off, yes, that's going to make the methyl radical, which is bad. But what's left behind is a secondary carbocation, right? This is secondary carbocation. That's a secondary carbocation. But you know that this secondary carbocation is way more stable compared to the other one. What is this thing? Resonance stabilization. So resonance structures, you cannot escape from it. So having methyl groups up make the allyl radical, allyl cation, and that's stabilized by it. So you're going to have this methyl group goes out really easy. I know methyl radical is bad, but what's left behind can compensate. So this is a spectrum of this molecule. You see that there's a molecular ion peak, 17. And then 55 is M-15. Methyl groups taken out is a base peak. That's a high peak. That's a more stable fragment because of the cation being stabilized by the resonance structures. So you can see that solution for the one problem doesn't apply to the next one because the structure changes. You cannot just memorize this thing. You have to look at the molecule, solve it based on the structures, not by the similarity of the structures.